Hello everyone, hopefully your revision is going well for the up and coming maths exams. I was looking through some of my old files recently and I found a full practice paper, and I thought it would be a good idea to go through it as a bit of extra revision, a bit of extra practice if you've covered all of the past papers already. When I wrote this, so long ago I can't really remember, I wrote it as easier. What that means is questions should have plenty of hints, and if you've not started revision yet, then you should still be able to attempt some of the questions and it'll be a good gap finder for you. Shall we dive in? So question 1 is about parametric equations. I know that because it says it right here. We're given x in terms of theta and we're given y in terms of theta, and we need to find a Cartesian equation. That means we need to get rid of theta. We only want x and we only want y. In order to do that, you've got to know that when it's trig related, you have to use some kind of identity. We've got sine, we've got cos. Can you think what identity we're going to use? I'm thinking sine squared theta plus cos squared theta equals 1. If x is equal to 1 plus sine theta, then we rearrange. We can get sine is equal to x minus 1. So sine squared is x minus 1 squared. Similarly, we know that y is 2 minus cos theta. Add cos theta to both sides, minus y from both sides. We get 2 minus y, and then square it for cos squared. That should still be equal to 1. What's interesting about this bracket, because it's squared, it doesn't actually matter if we write it this way or if we flip it around like this. I'm going to flip it around though, because now you'll hopefully recognize what this is. This is a circle. I'll draw a picture there if you're not sure what they look like. So we have found the Cartesian equation, which is this, and we have determined what type of shape the graph has, which is this. Now for part B. After reading through part B, I've already found a mistake. What fun, I've just changed it now. So the region that we're looking for is bounded by the top half of the curve C. So it's a circle. We're just looking at the arc on the top of the circle. It's bounded by the x-axis, it's bounded by the y-axis, and it's bounded by the line x equals 2. Let's draw a quick sketch to see what that might look like. So I'll draw my axes. This is a circle, but we need to actually know where it is. Remember that this number 1 and this number 2 represents the centre of the circle, like this, and this number over here, okay, we have to square root it, still equal to 1, that represents the radius. So the circle is going to go here. And the region that we're looking for, now that I've added in an extra bit, given that it was wrong, is the line x equals 2, which is here, x-axis, which is here, y-axis, which is here, and the top half, which is up here. So we're looking for this shape here, which we are apparently calling R. We need to show that the area can be written as an integral. So yes, you could just find the area of a square and add on the area of a semicircle, but this is testing how we're going to use the parametric integration. So we are integrating between x equals 0 and x equals 2, and we want the function y dx. That's how we usually integrate, but there are thetas about. We've got to do this differently. Why don't we divide by dt and times... Why don't we divide by d theta and times by the d theta? I've not changed anything because I've times and divided by the same thing. But now, if I rewrite the integral, y, according to the question, is 2 minus cos theta. Dx d theta is the derivative of x with respect to theta, which is going to be cos theta, d theta. If we now expand this out, let's see what we're going to get. 2 times cos theta is 2 cos theta. Cos theta times cos theta is cos squared theta, like this. You'll notice it's almost looking like what's in the answer here, but something's not quite right, and that's these xy limits. They need to be in terms of theta. So let's have a little think. At this point here, when x is equal to 0, that means that 1 plus sine theta must be equal to 0. That means that sine theta must be equal to -1. And if we think about the old sine graph, we know that that must mean that theta is equal to 3 pi over 2. There are negative values too, there are bigger values too, but we use the range of the values of theta to know that it must be 3 pi over 2. That was when x is 0, so I'm going to put this as the bottom limit. Next one, x is equal to 2. When is x equal to 2? X is equal to 2 means that 1 plus sine theta is equal to 2. Sine theta is therefore equal to 1. Use the same graph. Theta is pi over 2. Now I'm doing it in terms of radians. There's two reasons for that. One is it gives us radians in the question. There's pi's. Two is we can only integrate in terms of radians. So pi over 2, I'm going to jump up here and the top limit, and then I'm going to write everything else the same. Looking back at the question, is it exactly the same? Have we shown that it can be written in that form? Not quite. What's wrong? The limits are the wrong way round, and this is backwards. It's all negative. That's fine. That is just one of our rules. If you integrate something backwards, it's the same as adding a negative in to both terms. Like this. Which, okay, it doesn't look exactly like it. Maybe I'll do one more step. Just to put the negative on there. And now I can say, hey, look, I've shown that. Please give me 4 marks. On to part C then. Part C asks us, by using a double angle formula, write down cos squared theta in terms of cos theta. You might just know this formula, and that's great. If you don't know the formula, however, I will show you a way of getting it, such that if you're in your exam and you're panicking that you don't know it, you can derive it yourself. So if we get the trigonometric identities, then we'll be able to use this one here, which is in terms of cos, to be able to find the double angle formula for cos. How are we going to get cos of 2? I'll do it in terms of x for now. Well, what could a and b be? They don't have to be different. Why don't we make it cos of x plus x? That gives 2x. Using the formula, that tells us we need to do cos of x. You have to be careful here that this plus or minus is flipped. It's a minus plus. Because we did x plus x, we have to do a minus here. And then we have to do sine of a, sine of b. They're both x. So it's sine of x, sine of x. Let's simplify a little bit. Cos squared x minus sine squared x. What did the actual question say? Write down cos squared, find my mouse, write down cos squared theta in terms of cos 2 theta. So we don't want this sine squared knocking about. Why don't we use our identity? This is 1 minus cos squared x, which means that if we now simplify, that is 2 minuses, adds on a cos squared to get 2 cos squared x minus 1. So cos 2x is equal to 2 cos squared x minus 1. Still true if we put theta in here. But that's not what the question wants. The question wants cos squared in terms of something else. So we need to add 1 to both sides. And then we need to divide both of these by 2. And voila, we have cos squared theta in terms of cos 2 theta. If you did know that formula off the top of your head, great. If you didn't, you can realize there is a way to get it. You don't need to panic in the exam. You can always derive the formulas again. Okay, we shouldn't need that formula again. Let's get on to part D. Part D asks us to, hence or otherwise, show the exact value of the area of R is pi over 2 plus 4. Reading through this question again, I shouldn't put or otherwise in there because you can absolutely just do area of square plus semicircle. Let's do it hence. Let's use the integral. Let's integrate. So how do you integrate cos squared theta? Well, we didn't do this for nothing. We absolutely have to put in the version of cos squared theta in terms of cos 2 theta plus 1/2, like this. That's the only way to integrate cos squared theta. So as I was writing this 3 years ago, I obviously thought to make it easier, here's the hint, use the double angle formula. It's not always going to say that, so just have it in your head. If you ever want to integrate cos squared or sine squared, the cos double angle formula is the way to go. So now we can integrate. To integrate cos 2 theta, we need to think about what differentiates to get cos, and that's sine. So the answer to this is going to be sine 2 theta, and then we need to think about the constants. We've got a half already on the outside, and we need to divide by this 2 by the reverse chain rule. So we have a half and basically another half, which gives us a quarter. To integrate a half, we simply plop a theta on the end. And to integrate this, it's very much the same as the first one, but there's no 2 that we have to think about. So it's just minus 2 sine theta. And that's still between the same limits of pi over 2 and 3 pi over 2. I'm now going to come up here for a bit more room. We now need to sub in the top limit. Quarter sine of 2 lots of 3 pi over 2 is 3 pi, plus 1/2 3 pi over 2 minus 2 sine 3 pi over 2. Put that in some big brackets. Minus, I'm going to now put in the bottom limit, so a quarter sine of, is going to be pi, because it's 2 times pi over 2, plus plus a half pi over 2, minus 2 sine pi over 2. You probably just stick that on the calculator. I'm going to do it without. Sine of 3 pi is 0. Sine of pi is also 0. So what we're going to get is 3 pi over 4 minus sine of 3 pi over 2. We saw it, well, it's just up there, so you can't see it. But sine of 3 pi over 2 was minus 1. So this is actually plus 2. Minus 2 times minus 1. And then we're going to minus half times half is a quarter, so pi over 4. And then this is minus 2 times 1. That one you can actually see, it's just there. Expand out the brackets. 3 pi over 4 minus pi over 4 plus 2 plus 2, 2 negatives. That's going to give us 2 pi over 4 plus 4, which is going to give us 4 plus pi over 2. I thought the answer was the other way around. Pi over 2 plus 4. There we go. Well, that was a nice question 1. Let's move down to question 2, which has e parts. Lovely. In question 2, we are given a curve with the equation 4x cubed minus 3x plus 1. So I'm going to write that down. Seems like it's going to be useful. In part A, we are asked to verify that x equals minus 1 is a root of that equation. It should really say the equation that equals to 0. I'll change that at some point. To verify that something is a root, that's not saying show that it is a root, it's saying just check. And all we have to do to check is just sub in minus 1. So let's just see. 4 times minus 1 cubed minus 3 lots of minus 1 plus 1 is equal to 4 lots of minus 1 is minus 4. 2 negatives give us plus, which gives 0. It's only worth 1 mark, but we should therefore say, therefore x equals minus 1 is a root of the equation 4x cubed minus 3x plus 1. As I say, it should say equals 0 on there. Okay, I've corrected the error now. Only 2 mistakes so far, not too bad. Let's do part B, factorize completely. So to factorize completely, you may have a method where you can just write out one factor and then the quadratic, and then factorize the quadratic. That's fine. I'm going to do it with polynomial division just to show you that it can be done. With polynomial division, if x equals minus 1 is a root, we need to add the 1 to both sides to show that x plus 1 is one of the factors. If x plus 1 is one of the factors, then what do we times x by to get to 4x cubed? That's going to be 4x squared. Now if we times 4x squared by this, we get 4x cubed plus 4x squared. Subtract, that disappears. There's technically a 0x squared in there, which I'm going to do 0 minus 4 to get minus 4x squared. And then I'm going to bring down the minus 3x and the 1. I really should have left a space for x squared there. I should have seen that coming. Oh well. What's next then? How do we get minus 4x squared from x? We times by minus 4x. Minus 4x squared. Then we do minus 4x times by the x to give us this, and minus 4x times by the 1 to give us this. We subtract again. They should disappear. Minus 3x minus 4x should give us plus x. And then, whoop-de-doo, we get plus 1, which means there is no remainder, which seems good. We got a remainder, we'd be a bit stuck. So this means that the original cubic can be written as x plus 1 multiplied by 4x squared minus 4x plus 1. Then we look at that one and we think we can factorize it. 2x minus 1 minus 1. Or, if I'm really feeling like it, I'll put the squared bracket on. Either answer there, they're both fully factorized. What do we want to do in part C? Find the coordinates of the stationary point. So, okay, I've not given a hint here, but if you see the word stationary point, it's about differentiating. So let's differentiate. dy dx from the very original is going to be bring down the 3, times it by the 4, and then take 1 away from the 3 to get 2. Then the next term is going to be minus 3. That's because the x is already a power of 1. It becomes a power of 0, which is just a constant, just 1. And then any constant just disappears. 12x squared minus 3. And because it's a stationary point, SP, it implies that the derivative is 0. That's because at a stationary point, the derivative is flat. So dy dx has to be 0. Let's now solve this, see what we get. 12x squared minus 3 is equal to 0. 12x squared is equal to 3. X squared is equal to a quarter, so x is equal to a half. Plus or minus, don't forget that. You've got hints in the question. If I can find my mouse, it says stationary points. It's plural. That should help you remember that there should be a plus or minus here. So we've got x is half, it's minus a half. Are we done? Not yet. We want the stationary point. We don't want the x coordinates of the stationary point. We want the actual point. So we need the coordinates. So when x is equal to a half, what's y? Well, look at this. We've got the equation of y in terms of x, so we just sub it back in. So sub it in here. Let's see what we're going to get. That's going to be an eighth times by 4 is a half. A half minus 3 halves is minus 1, plus 1 is 0. Didn't expect that, but that's cool. When x is equal to minus a half, again, I'm going to sub it in. Here and here, plus 1, which is 2. So what are the stationary points? They are, I'll call them A and B. They are 1/2, 0, and minus 1/2, 2. Now let's sketch it for part E. In order to sketch it, we of course need some axes. So the curve is a cubic, which means it's either got this shape or this shape, depending on if it's a positive cubic or a negative cubic. This cubic starts with a 4, so it's going to be a positive cubic, and it's going to be this general shape. We know the stationary points as well, and we also know the roots. We know the roots because we have one here, and we have the other one from here. So x plus 1 as a factor means that x equals minus 1 as a root, and then the other root is from here, x equals a half. So that means that one of the roots is going to be here, minus 1, and the other is going to be here at a half. So I'll just draw the general shape in like this. Because the half was a repeated root, that means when we get down to a half, we're going to spring back up. We're not going to go below. Imagine this, if we go below the x-axis as a half, we need to go back up again. Well, where's this root in the factorization? It's not there. So we have to go to a half and then shoot back up. We also know that this was a stationary point, according to what we just did, 1/2, 0. And we also know that this stationary point here is at 1/2, 2. The last thing we know is that this point here, I've clearly not drawn it very well, but this point here should be 1, because that is when x is equal to 0. We have 1 left over. There we go. That's a bit of a better diagram that's a bit more accurate. As long as you've labelled it, you'll be fine. You get the 2 marks for this. Okie doke, question 3. A curve has equation y squared equals x cubed. I'm going to write that down because I can. By implicitly differentiating both sides of the equation, show that the derivative is 3x squared over 2y. In order to implicitly differentiate, that means we just differentiate as if it were x, and then we pop dy dx on the end. It could be a product, which looks like we'll see later on, but for the most basic, implicit differentiation when it's just something in terms of y, differentiate it as if it were x, put dy dx on the end. It uses the chain rule. To differentiate x cubed, bring down the 3, take 1 away from the power, and look at this. Well, just about there, we have now shown that if we divide by 2y, hey presto, we've got the answer. 3 marks. I'm not sure why I gave 3 marks for that, but hey, I'll take it. Part B, find the gradient of the tangent to the curve at the point on the curve where x equals 1. That's a bit of a mouthful. We know x is equal to 1. Do we know what y is? Y could actually be one of two things. Y could be plus or minus 1, because y squared would be equal to 1. That means that dy dx is going to be equal to 3 over plus or minus 2, or plus or minus 3 over 2. Okay, just quickly change the question from x equals 1 to y equals 1. Now the y equals 1, that means that y squared is 1, that x has to be 1, not plus or minus, which means specifically the derivative is now the positive version, 3 over 2. We're looking for the equation of the normal line, but that's the derivative. That's the tangent line. So what we need to do is we need to flip it to get the perpendicular gradient, which I call mperp, which is going to be minus 2 over 3. Then what we can do with that is we can use y equals mx plus c if you like. I'm going to use y minus y1 equals mx minus x1. We know that y and x are both 1 at this point. So that means let's times by 3. Let's expand the bracket. Let's write the equals. Let's bring x onto both sides and then minus 2 on both sides. And let's make sure it's in the right form. No, it's not. I need to read these questions before I actually start assuming what they want. 3y plus 2x equals 5. Perfectly the same. We get 3 marks. Nicely done. Part D looks like it's related to the same topic, but unrelated to the original curve. We've got another curve. This curve is a bit more funky. X's and y's are now times together. We want to find the derivative. The idea is still the same. We need to implicitly differentiate. But here, because they're times together, you have to use some sort of product rule. To do the product rule, we can let u equal the first thing and v equal the second thing. So 2x and then y squared. Alternatively, it could be x and y squared and then you just times by 2. No problem with that. So I'm quite lazy. I just use u dash and v dash. You can use whatever notation you prefer. My dashes here are implying it's to do with x, but if you do the notation du dx, then it does make it a bit clearer. What's the derivative of 2x? That's simply 2. What's the derivative of y squared? It would be 2y if it were with respect to y, but it's not. It's with respect to x, so we put dy dx on the end. So that means the derivative of this, there is a formula, but you do not get this given. It's a crisscross type of thing. 2x times by 2y dy dx. So 2 times 2, 4, and then xy dy dx, and then you add on these two, which is 2y squared. So that's the derivative of that. The next one, I'm going to differentiate in a bit of a quicker way. So I'm going to write minus 3 and then a bracket. The other way that you could differentiate is by writing down one function, x squared, not changing it, and then differentiating the second function, which would be dy dx. Adding, because it's the product rule. Write down the second function, which is just y, and then differentiate the first function, which is x squared, like this. So it's a simpler way of doing it. It's more of a wordy way. Write down the first, differentiate the second, write down the second, differentiate the first. But there's also the product rule, there's also the u and v version. Use whichever one you prefer. Now we've differentiated the left, we also need to differentiate the right. The derivative of x, or 1x, is just 1. Let's put this all together then. We've got dy dx twice, so I'm going to combine those together on one side. Everything else I'm going to send to the other side. So I'm going to minus 2y squared, and I'm going to plus that's going to be 6xy. If we want dy dx, and we don't want anything else, why don't we factor out these things that we don't want? And then that's going to pretty much give us our answer. Dy dx is equal to the right hand side divided by the left hand side in the bracket. Just comparing it to the answer given, the 6xy and the minus 2y squared are in a different order. I'm not going to bother rewriting it this time. That's good enough for me. I have shown it. All right, question 4. We are binomially expanding. We want 2 plus 3x to the power of 5. In order to expand 2 plus 3x to the power of 5, we need to know about binomial coefficients. We need to know that 5 choose 0 times by the first term to the power of 5 times by the second term to the power of 0 is going to give us the first term of the expansion. Now you don't really need this and you don't really need this because they're equal to 1, but it gives a nice pattern. You'll notice as we do more and more terms, these two numbers will add up to give 5, and this number will be going 0, 1, 2, 3, 4, 5, so in order. So the next term, 5 choose 1, 2 to the 4, 3x to the 1. So 0 and then 1, and the next one's going to be 2, and then 5 and 4, and the next one's going to be 3, 0, 1, the next one's going to be 2. 5 choose 2, 2 to the 3, 3x squared. 5 choose 3, 2 to the 2, 3x to the 3. 5 choose 4, 2 to the 1, 3x to the 4. 5 choose 5, 2 to the 0, 3x to the 5. Simplify all these. Let's see what we get. As I say, that's just 1, so that's going to be 32. The next term is 240x, then 720x squared. Common mistake here is not putting the 3x in brackets, so make sure that's 3 is squared when you do the coefficient. Then 1080x cubed, then 810x to the power of 4, and then finally 243x to the power of 5. So for something like this, for me it's very methodical. Get the patterns 0 to 5 or 5 to 0 depending which way. Calculate all those numbers and you get 3 marks. In part B, which I'm going to write here because I've not got much room, the binomial expansion of a plus bx times by 2 plus 3x to the power of 5, we are told is 32 plus 176x. We're not told any more terms. We don't need any more terms. And here it looks like it gives us a hint. By considering just the first 2 terms of the expansion that we just found, or otherwise, so do it another way if you want, find the values of a and b. So I'm going to use the hint, given I wrote it. 2 plus 3x. We only really need to consider 32 and 240x. I'm going to put a plus ... here, just to signify that there are more terms. We just don't need to consider them. Now when you think about expanding the brackets, you can almost just treat this as a normal 2-bracket expansion. Yes, there's plus ... but all those extra terms are going to have a power of x that's too big, that we just don't care about, that's in this ... So why bother doing it? Let's see what we're going to get. We're going to get a times 32, so 32a. We're going to get 32 times by b times by x here. We're going to get a times by 240, so 240x. And even this term, x times x, is going to give us x squared. We've not even written that down, so there's no point bothering. All we need to compare are the constant terms and the x terms. Let's compare coefficients. 32a is a constant, 32 is a constant. Well, this just means that a must be 1. Now comparing x terms, 32b plus 240 is going to be equal to 176. The coefficient of the x terms on the left should be equal to the coefficients of the x terms on the right. I'm going to guess it's going to be -2, but I'll just check. Yes, I obviously made this with nice solutions. B is -2. Looking at the next question, it's still related to binomial expansion, but this time there's two differences I see. It's got a -2, so we have to use the alternative binomial expansion formula. And it's also got an unknown letter inside the expansion. So we might be doing this in a slightly different way. Let me get the formula up and we shall have a look. Okay, I pasted the formula in here. I've also remembered, obviously forgot that you get the formula for the first style of question. So if you don't remember that methodical way of doing it, you can absolutely use this formula. You might also remember the second formula. It's quite helpful if you do, because it could be confusing when you're reading it like this in terms of R's and things. But I'll go through using the formula for this question. We are looking for the expansion of 1 plus px to the power of -2. First thing you have to note is that this is just x. So if this is px, you have to put all of these x's here and here and here in brackets with px. So px squared or px cubed in a bracket. In this question, we're only looking for the third term. So it can be quite tricky to see where that's going to come from because it's plus ... But the pattern is we take the power, then we take 1 away, and then the next one will be we take 2 away, then we take 3 away, then we take 4 away. And in the denominator, we do 1 times 2, and then it'll be 1 times 2 times 3, then it'll be 1 times 2 times 3 times 4. So in that pattern. It doesn't show that next one, so you have to understand what it's trying to say. So the third term, well, actually, technically it's the fourth term. Let's say the x to the power of 3 term will be n, which is the power, so -2. Take 1 away to get -3. Take 1 away again to get -4. Divide it by 1 times 2 times 3. Then times it by x, but x is actually px, and raise it to the power of 3. Now let's simplify this. That 3 and that 3 will cancel, that 2 and that 2 will cancel, that negative and that negative will cancel, and we're going to be left with -4p cubed x cubed. And we're told in the question that the coefficient is 32. But that doesn't mean that this is true. If the coefficient is 32, then that actually implies that this is true. You can either compare with x's or you can compare without. You can't have the left-hand side with x's and the right-hand side without, or vice versa. So let's solve this. We're going to now divide by -4 and then take the cube root. We get another lovely answer. P is equal to -2. Okay, last part, only worth 1 mark. Students do seem to struggle with it though. For what values of x would this is a different binomial expansion now, this be valid? We take a modulus, we put the x bit in, we say it's less than the number bit next to it. That comes from this formula down here. Sorry about the 2 cursors, this one at the bottom. I've taken the x bit, which is at 3x, and I made it less than, well, usually it's 1, but in this question there's a 2, so I made it less than 2. That usually would be enough, but if you really want to put it in a nicer form, you could say that the modulus of x is less than 2/3. So it's only 1 mark, it should be a nice easy mark, but students sometimes have trouble with it. Who's ready for a bit of proof? I know that's pretty much everyone's favourite topic. We want to prove that the sum of 2 odd numbers is an even number. Let's take 2 odd numbers. What does an odd number look like? It's of the form 2m plus 1. Any odd number can be written in that form. Maybe another mistake with this question, rather than saying number, I should probably say integer. Right, change the question to integers. Let's change this to integers. 2 odd integers, well, one of them is 2m plus 1. The most common mistake I see here is writing, for example, 2m plus 3. These are not 2 arbitrary odd integers. It's 1 odd integer and then the one that follows after it. You have to write this as a completely different odd integer. Otherwise, all you're proving is that if you've got 2 odd integers next to each other, then it's even when you add them. But the question is saying that the sum of 2 odd integers. It doesn't specify where they are. They could be any odd integers. So I like to choose a different letter. This is odd, different letters, different odd numbers. This means that the sum is going to be 2m plus 1 plus 2n plus 1, which is 2m plus 2n plus 2, which is equal to 2 lots of m plus n plus 1. And this is even. Why is it even? It's because it's of the form 2k. So it's of the form 2 times something, so it has to be even. That's the proof done. We've added together two odd integers, two arbitrary integers, summed them together. We've got something that's even, therefore that's done. 2 marks. Part B is a counterexample. So what we need to do is we need to find just one single example where the square root on the left is not equal to the numbers on the right. We could try x is equal to -1 and also y is equal to -1, and we'll see that it won't work. The square root of -1 squared plus -1 squared is equal to the square root of 1 plus 1, which is the square root of 2. But that is not equal to x plus y, because x plus y is equal to -2. Now you don't have to use negatives here, but it's good to get into the habits of using negatives when you see a square root, because those are often the ones which give you the counterexample. Okay, question 6 looks like a short one as well. We are asked first of all to solve this equation, so 6x squared plus x minus 1 equals 0. Loads of ways of doing it. You could complete the square, you could put it into brackets, you could cheat with the calculator, but you do have to make sure that you do write it with some sort of working. So even if you just pretend to use the quadratic formula, sometimes they do want you to have a bit of working there. I'll put it into brackets. We get the solutions. When the left bracket is 0, x is a third. When the right bracket is 0, x is minus a half. Hence, solve the inequality. We know that the roots are a third and minus a half, and we know it's quadratic, so it should have a smiley face. Not a sad face, because 6 is positive. So let me just label that, minus a half and 1/3. When is the inequality bigger than or equal to 0? It's when the curve is bigger than or above the x-axis. So it's here and here, all the way up there. So what are the values for x? Well, it's 1/3 and all the way to the right, and it's minus 1/2 and all the way to the left. So we have x is less than minus 1/2, or x is bigger than a third. But we're not done there, because it says write your answer using set notation. So we draw a squiggle, an x, and 2 dots. We draw another squiggle, another x, and another set of dots, and we just copy and paste this in. Copy, paste, like that. The only other thing is that we actually need this OR symbol. Think back to probability. What's the OR symbol? This one. So between the two sets, we say union, one set or the other, and that would be it for our set notation. In question 7, we are asked to estimate the value of the integral by using the trapezium rule. Usually my least favourite subject, because I like exact answers to integrals, but obviously I wrote this question. In order to do this, we need to know the formula. Here we go. Here's the formula. Integral from a to b of y dx is equal to this whole thing. So obviously the formula doesn't really explain what things are. So you not only do you have to know to use the formula, you have to know what things mean in the formula. It tells us that h is equal to b minus a over n. B and a might be easy enough to work out, because they are the limits of integration. So here a is 0 and b is 1. So if we want h, this will be 1 minus 0 divided by n. Doesn't say what n is. If we use the question, you might be able to work out that n actually represents the number of strips. So in this case, h is equal to a quarter. The formula doesn't even say what h is though. What h represents is the width of each of the trapezia that we're finding the areas of. So if I do a quick sketch, I don't really know what this function looks like, but let's do it like this. we're integrating between 0 and 1, and it's telling us that there's a 1 quarter, and then another quarter, and then another quarter, and then another quarter, and we are finding the trapezia in here like this, just about. That's our goal. In the formula, it doesn't really explain what y0, yn, y1, y2, yn minus 1 are. They represent the y values for the certain x values. The first value is actually y0. Now that's a bit annoying. The last value is yn. I quite like to put this in a table. Let me draw one out. So here's my table. N goes from 0 to 4, where 4 is the number of strips. X goes from 0 to 1, because those are the limits of integration here. And the difference between each value of x is h, which we calculated over here. Y is the value of the function evaluated at that x. So 3 times 0, square root 0 squared plus 1. That's just 0. So it means that this is just completely nonsense, but that's just 0. Similarly, 3 times 1 is 3, times the square root of 1 squared plus 1, we get 3 square root 2. All the other ones in the middle probably aren't going to be so nice, but I'll work those out and I'll add them into the table. Okay, got all my values there. I'd just like to show you one of the things I quite like to do is using the table function on the calculator. If I type in what x should be and click equals, equals again because I don't want g, start at 0, end at 1, make the step 1 quarter or 0.25. And what it does is it just tells me all the values of y straight away. That last one there, it doesn't actually come up with the square root, but that is the same as 3 root 2 over here. So next we need to shove it into that horrible formula. The formula tells us that the integral, I'm just going to call it the int, is equal to 1/2 h. h is a quarter, so 1/2 times 1 quarter, times by, I'm going to do a big bracket. Students don't often realise that that curly bracket down here ends all the way over here. So make sure everything is in one really, really big bracket. When it says y0 plus yn here, I like to think of that as the first and the last value. I don't think about it in terms of 0 and n, I think about it as first and last. And then we have to add on two lots of what? 2 lots of everything else. Again, I don't think about it as y1, y2, y3, yn minus 1, it's just everything else. So it's going to be 0.77 dot 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 plus 1.67 dot 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 plus 2.81 dot dot dot. Once we shove that all into the calculator, we'll have our final answer for the integral. And I get this, 1.845988408. If we read the question again, it asks us to round it to 3 decimal places, which I'll do 8, 4, 6. So that's how you do the trapezium rule. Yes, you have the formula, but you also have to know what all those letters mean and how they go together. To make up for the inexact answers of part A, just rounded, how boring, now we're going to use some sort of integration technique to find the exact answer for the integral. My suggestion there is, by reverse chain rule or the substitution, I'm going to do the more methodical substitution method, because students sometimes can't get on with the reverse chain rule. The substitution it tells us is u is equal to x squared plus 1. It's not always given. So try and work out why that would be a good substitution. In order to substitute, we have to differentiate this substitution. du dx, that's the proper notation. Differentiate 2x, that disappears, so plus 0. We also want to rearrange this to get dx equals, and in this case we're going to get 1 over 2x du. The reason why we want to do that is because this is dx, but our substitution is going to be in terms of u. I'll do the limits afterwards, but I'll put this in now. So we've got 3x times by the square root of, well, it's u, times by dx, but it's not dx, it's actually 1 over 2x du. These two cancel, and that gives us 3 over 2 square root u. If we want to integrate the square root of u, then we can make it u to the power of 1/2, and then follow our usual rules. add 1 to the power and then divide by the power. Alternatively, times by the reciprocal. Well, this and this cancel out. Lovely, we get u to the power of 3 over 2. Plus c, because I haven't done any limits. But what's nice about this is, I don't actually need to change the limits at all. If I rewrite this in terms of x squared plus 1 to the power of 3 over 2, then I can leave my limits in terms of x. It's still x is 0, it's still x is 1. You absolutely could change them, but if you don't like changing them, why bother? So leave it as x equals 0, x equals 1, all the way down, all the way down. You don't need a plus c in the end, because you've got the limits 0 to 1. Let me know down below if you prefer to change the limits or not. So the exact value of the integral is going to be 1 squared plus 1 is 2. That's 2 to the power of 3 over 2. Minus, that's going to be 1 to the power of 3 over 2. So just, it's supposed to be a 1. But this power over 2 represents a square root. So this is actually 2 root 2 minus 1. And that's the exact answer. Oh, and it's in the question. I didn't even see that. 2 root 2 minus 1. Lovely. I didn't read that this was even a show that, so I'll just take another second to say why this is true. 2 to the 3 over 2 is the same thing as 2 to the power of 3 under a square root. But you can split apart that square root like this. So 2 squared times 2. But the square root of a square is just 2. So that's 2 root 2. I know I wrote this question, but let's say the examiner wants a bit more detail. That's how you could show that it's 2 root 2 minus 1. Right, we're about halfway through, and question 8 looks quite long, so I'm going to take a break. Maybe you should too, and I'll see you again after my break. And now we can continue with question 8. In question 8, we need to separate the variables to solve the differential equation dy over dx is equal to x over y. By separating the variables, that means we need to put the y bits on the dy side, and we need to get the dx on the x side. So we times both sides by y, and we times both sides by dx like this. We add the squiggle of integration, and now we integrate both sides. Y squared over 2 and x squared over 2. At this point, we want to add on some kind of constant of integration, call it c. It doesn't matter where that c is, it could be on the left, it could be on the right. If you add it on both sides, you need to call it a different letter, so a c and a d. I just put it on the right hand side, just do it once. Let's now times everything by 2, like this. And now that answer is in the form y squared equals some function of x. So that's our final answer for part A. As for part B, this time we've got a different differential equation. dy over dx is y over x. Chances are in an exam you wouldn't get 3 parts like this A, B and C with different differential equations, but it's good practice if you can do it 3 times so you can understand the skills involved. We are still going to separate the variables. This time, to get the y on this side, we need to divide by it, like this. To get dx, there's no difference in that one. So we get this. We add the squiggle of integration. Now to integrate 1 over y, that's ln y. And that means it's the ln x on this side, because it's the same thing, but with change of letter. And then, as before, I'm going to add my c over here. Technically, there should be modular signs here and here. Sometimes the question needs it, but sometimes it's defined only for positive values. In this case, we're given that y is 8 when x is equal to 1, so we're given a boundary condition. Y is 8 and x is 1. Well, that means that ln of 8 is equal to ln of 1 plus c. Ln of 1 is just 0 though, so that means c is equal to ln of 8. Therefore, ln of y is ln of x plus ln of 8. But this is laws of logarithms now. When you add together 2 logarithms, it's the same as multiplying what's inside them. And because there's 1 logarithm on the left and 1 on the right, you can get rid of them. So y is equal to 8x. And then the third differential equation, as if 2 isn't enough, we've now got dy dx, and this time it's equal to x, y. I'm going to follow the same process. I'm still going to times by dx on both sides, and to get y on this side, I'm going to divide by it. We're going to integrate. We're going to get ln y again on the left-hand side, and on the right-hand side, x squared over 2. I'm still going to add on a plus c. In this question, it doesn't have any boundary conditions, so there's nothing more we can do. But what we can do is write it in the form it wants, which is y equals. So y equals, how do we get rid of the ln? We do e to the power of both sides. So we do e to the power of x squared over 2 plus c. This last step, if you've not seen it before, it might be tricky to understand, but it is quite common. We rewrite this using our laws of powers, e to the x squared over 2 times by e to the c. And what we do is we pretend e to the c, well, it's still just a constant. So we call it a instead, like this. And now that's of the form it wants. So as required, we've shown it's of that form. A is just another constant. You don't necessarily need to say a is equal to e to the c. You could do though, no harm in it. In number 9, we've got a population of frogs in a certain area, and after t years, it's got this equation where p is equal to 550 e to the power of 0.1 t. Part A asks us to write down the initial population of frogs. So if it says write down, it means the answer is going to be somewhere in there. In fact, the answer is right there, 550. If you couldn't see it straight away, then the idea is initial means at the start. The start, t is 0. If t is 0, then this is 0. E to the power of 0 is 1. 550 times 1 is 550. Once you've seen it once, you've seen it all the times. The answer to part A, just 550 frogs. For part B, after how many years will the frog population have doubled? Well, if it starts at 550 and it's now doubled, it's now 1,100. That's the population, and we know that the population is equal to 550 e to the 0.1 t. That means if we divide, we get 2 is equal to e to the 0.1 t. We can then take a natural logarithm on both sides, like this. That's equal to 1 over 10, so t will be equal to, times by 10 on both sides. So t is 10 log 2. 10 ln 2 is equal to 6.93. So after how many years will it have doubled? We can say after 7 years if we round it. As for part C, find the rate of increase. So as soon as I see rate of increase, I make the association with the derivative. In this case, it's not dy dx, but it's dp, because it's the rate of increase of the population, and it's dt, because you're imagining the rate is increasing over time. In order to differentiate this, we need to take this power and times it here, and then this e term stays exactly the same. So that's by the chain rule. So it's basically timesing this by a tenth, so 55 e to the 0.1 t. It says find the rate of increase, done, after 10 years. So that means t is now equal to 10. So that means the rate of increase dp dt is 55 e to the 1. So 55 times 2.7, 1828, 1828, or 59045. Anyway, we get 149.505, 5006. And if we give that to three standard figures, I'm not sure what that means. Probably should say 3 significant figures, interesting. Then that would be 150. And finally, give one problem with the model. So equally that could say critique the model or criticize the model. I won't bother writing it down, but the model doesn't really say it's going to stop at any point. Over the time, it's just going to increase and increase and increase. That's not really likely. Why is that not likely? Well, first of all, some of the frogs might die out and the model doesn't include that. Or there may be some other kind of predator that eats the frogs, gets in the frog's way, that means it doesn't just keep on increasing and increasing forever. Question 10 says the graph cos of x is translated by 30 degrees to the left and then stretched by a scale factor of a half in the y direction and we need to write down the equation of the transformed graph. So remember that when you are moving to the left or to the right, it happens inside the bracket. What happens inside the bracket is also backwards to what you might expect. So if we're moving to the left, you'd think it might be minus, but it's actually plus. And it's plus, in this case, 30 degrees because it moves 30 to the left. If it's stretched by a scale factor of a half in the y direction, all we do is put a half on the outside. It's not backwards, just put the number on the outside and then that's done. And I'll call it y. That is the transformed graph there. For part B, it's stretched by a scale factor of 3 in the x direction. If it's in the x direction, then it's what's happening inside the bracket. So usually we say f of 1/3 x. We can't write 3x because it's inside the bracket, so it's the opposite of what you might think. So in order to finish this up, we'd need to write 18x over 3 squared minus 33x over 3 plus 5. And I wrote this question, so I'm not saying you have to simplify, but I probably would. So I'm going to get 2x squared minus 11x plus 5 in this case. If it was stretched in the y direction, all you do is times everything by 3. But because it's in the x direction, you take each x, divide each x by 3, and then simplify it if you want. In question 11, we have a point P with coordinates 3, 0, and it lies on a circle. So let me quickly write down that circle equation. So if I draw a quick sketch, I don't exactly know where the circle will be. There'll be some kind of circle, and there'll be a point somewhere down here, 3, 0. Maybe the centre's about there. And we have to find the tangent which passes through 3, 0. I don't know much about the circle yet, so my first goal will be complete the square, find what the centre is, find what the radius is. To complete the square, I'm going to take the 2 and I'm going to half it. And then I'm going to subtract 1 squared. For the y's, I'm going to subtract 2 because I'm halving it. And then I'm going to subtract minus 2 squared, which is 4. That should be equal to 15. So x plus 1 squared plus y minus 2 squared is equal to 20. And that tells me what the centre is. The centre is minus 1, negative of 1, and then 2, negative of minus 2. The radius is equal to the square root of that number on the end. Don't think we'll actually need the radius, but it could be a question where you need it. So in this case, yes, my diagram is wrong. Minus 1, 2 is the centre here. It doesn't really matter. The maths will work itself out. We can find the gradient between these 2 points using our good old formula, y2 minus y1 over x2 minus x1. So 0 minus 2 over 3 minus 1. That'll be minus 2 over 4, or minus a half. That's the gradient between these 2 points here. That means the gradient of the tangent will be the negative reciprocal of that, which will be 2. This time, I'll use y equals mx plus c. We know what m is. We've just found it. It's 2. Do we know what c is? Not yet. We need to find it. We know what x is, though, and we know what y is. So if we put y as 0, and we put x as 3, we can very easily say that c is minus 6, and therefore the equation of the tangent line is 2x minus 6. Just like this. Question 12 is just a one-liner. Solve the trigonometric equation 2 cos 2x equals 1, and we're given the range 0 to 360. In order for us to solve this, we first need to divide by 2. Cos 2x is equal to a half. Once we've got cos 2x is equal to a half, we need to find the principal value for which cos 2x is equal to a half. And to do that, we can just put it into the calculator. That should give us 60 degrees if my exact trig values don't fail me. There's another one though, and the other one, you can either do it from the cast diagram, you can do it from the cos diagram, you can do it from a formula if you want. We're going to get 300 degrees. That doesn't answer the question though, not quite. We're looking for x, but this is not x, this is 2x. So what I'd say is let's times this by 2, like this, and see if there are any more solutions. And there are, in fact, there are more solutions. Once we've got these two, we can just keep adding 360 to them and seeing if they are still within the range. We add 360 to this, we get 420. That's still in the range, so it's good. If we add 360 to this, we get 660. That's still in the range, that's pretty good. If we add 360 to this, then we're bigger than 720, so we're not going to bother going any further. Final step then, we wanted x, so let's divide all of these by 2. 30, 150, 210, 330. There were our 4 solutions for 3 marks. Last question then, question 13. Got a bit of numerical methods. Not my favourite. We've got x cubed minus 8x plus 1 equals 0, and we've got to show that there's a root between minus 2.9 and minus 2.8. The easiest thing to do when you see 2 numbers and an equation, sub them in and see what happens. It might jog your memory about the method that you need to do. So I'm going to sub that in, 2.9, and then I'm going to sub this in with minus 2.8, and let's see what we get. We get minus 0.189 and 1.448. That might trigger what you need to do because one of them is positive and one of them is negative. So this top one is negative, the bottom one is positive, and you need to write a sentence something like, there is a change of sign, and the function is continuous, therefore there is a root between minus 2.9 and minus 2.8. So I know it's a bit of a wordy question, but if you want to get the marks, you have to write that wording down. I'm just looking at the marks I set here. Probably it would be worth 2 marks if this came up on your actual test. For part B, it looks like we're doing a bit of rearranging. We've got x cubed minus 8x plus 1 equals 0 again, and we need to rewrite it in the form x equals the cube root. Given that it's got the cube root, we definitely want to leave the cube as it is and move everything else over, like this. And then we can actually take the cube root. So x is the cube root of minus 1 plus 8x. And then if you really want, write it in the form that I've asked for, swap around the 8x and the minus 1. For part C, now we actually do something a bit more useful. We use the iterative formula, which is based off what we did in part B. We have the starting value minus 2.8 given, and we need to find an approximation of the root. So let's see, we've got x0 is equal to minus 2.8. I'm going to take that, pop it into the calculator and click equals, so it's saved as my answer. Then I'm going to do the cube root of 8 answer minus 1. This is my next approximation, so this is what we'll call x1 minus 2.86 blah 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 blah. This question doesn't specify how many times it wants us to do the iterative formula. So for this one, I'd spam it a few times. At some point it's going to stop. Can you see I'm still pressing equals? Well, you can't see I'm pressing equals. I'm still pressing equals. The actual number is not changing, which means that the actual solution, I'll call it x star, is minus 2.8889694001. Our question wants to give it to 3 decimal places, so 2.889 should be good. And that's the last question on the paper. Well, there we have it, 13 more questions complete. Let me know how you get on down below. Well done if you've made it all the way through the video, and I'll hopefully see you in the next one. Keep up with the revision.